lucky accident that happens to torture students, okay? So let's actually get into some real material. I'm going to share the whiteboard, um, and we'll be able to actually start discussing topics. Okay, so hopefully you can see that the white on the screen. Okay, and I have to do, since we're starting from scratch, I have to do some definitions. And the first definition I'm going to do is a set. And a set is something we talk about all the time. And a set is basically uh, like a list. And it could be a list of numbers or letters. Sometimes it's a list of symbols, but that's kind of more rare. But it's usually just thought of as a list. Now, it could be, like I said, of numbers and let's say and letters. Okay, sometimes symbols, but less often is it just symbols. Now we will usually use these funny little brace. We call this a brace to signify that this is a list. So maybe my list is 1, 2, 3, 4, A, B. This is a good example of a set. This is a set. We have some numbers, we have some letters, um, and this is an example of a set. These braces here, that's what we call these. We have an open brace and a closed brace, and this signifies that this is a list, and these are commas in between, and it's just listing things. Now, we have grocery lists, right? Grocery lists are a list, and a grocery list is also a set. So that would also be a set. And maybe later we'll talk about sets with states or sets with people's names. But in the abstract sense, we usually just do letters or numbers. And so a set is just kind of like a list, okay? The next thing that I want to define is called element. Okay, so an element is a object or an item in a set. So it's an object. Oh, we can also call it item. Maybe it's an item on your grocery list. Object or item in a set. Okay, so what is an element? An element in this set? Well, 2 is an element in this set. So this would be an example of a set. An example of an element is 2 is an element of this set. And we even have like a special symbol for element. It's this funny looking E there. And so 2 is actually an element of this set. It's an item. And so if it was a grocery list, maybe bread would be an element on our grocery list, but just in kind of this abstract example here, this is 2 is an element of um, that. So these are super important, okay? And I don't think I mentioned it before, but I will post all of these notes. Once I'm done tonight, I'll post them all after class. So the computer will save them for me. What else do I want to mention about elements? Well, we have this element symbol. Okay, this means element of. Okay, so 2 is an element of this set. Well, of course, we can see it right there. So, of course, it's an element. We also have this symbol, which we don't use as often, but sometimes we do. And it's the element symbol. And we just kind of cross it off there. And that would be not an element of. Okay, so let's think of an example. What's something that's not an element of this set? Well, the number 5 is not an element of this set. 1, 2, 3, 4, A, B. There's no 5 in this set, so 5 is not an element of that set. So, those are just simple examples, but sometimes we use this element of symbol all the time. If it's crossed off, that just means not an element of. We don't use that as often, but it will come up in the homework sometimes, of course. What else do I need to talk about as far as elements go? I don't want to do too many trick questions. Maybe I'll do another example. So let's say B is definitely an element of a set that only contains B. So if something, just because it's by itself, well, it's still contained in there. So B is an element of the set that contains B, okay? Hopefully, that's just symbols and notation definitions. It's nothing too bad. So hopefully that makes some sense. I'm going to keep going. Next thing that I want to talk about is called the empty set. So the empty set is a very special set. It's so special, it has its own symbol, which is like a little O with a cross out. So it's crossed out. This is the empty set. And the empty set, well, it's a set that's completely empty. There's no objects, no items, no objects, which we call elements, in the empty set. Okay, so the empty set is so important that it gets its own symbol, and that's its symbol. If I wrote out the empty set, well, it would be open braces, closed braces. That's it. And there's nothing inside. It's not even zero. There's not even a zero there. There's 0 things inside, but there's not even a 0 inside. It's just totally, totally, totally empty, okay? So the empty set. We'll talk a lot about the empty set. You wouldn't think there'd be that much to talk about since there's nothing inside it, not even the number 0. But yeah, we'll talk more about it in just a minute. But it's so special that it gets its own symbol. We do have sets that can equal just like our arithmetic, like 2 + 2 = 4. Sets can equal each other. We use the exact same symbol for, I don't want to use that symbol. We use the exact same symbol as we used before, the equivalent symbol. So an example of this might be that 1, 2, 3 is equal to 2, 1, 3. Now, how can that be? Because this is 1, 2, 3, and this is 2, 1, 3. And these are equal. And with sets, the order doesn't matter. We just can't have any repeats, okay? So 1, 2, 3, the set that contains the number 1, the number 2, and the number 3 is the exact same thing as the set that contains 2, 1, and 3, okay? And that would also be true with the set that has 1, 2, 2, 3. Because in sets, we don't actually write anything twice. We don't duplicate things like this. So we don't write it like this. I'm going to cross this out so I remember I don't write things like that. But it is totally equivalent to this statement. Okay, 1, 2, 3 is the same thing as 1, 2, 2, 3. But we don't write it like this. We don't double up like that. So we can see that that's true. But yeah, so that's sets equaling each other.
Professor?
Okay? Yes, sir.
You said that the sets are equal, just no repeats, correct?
That's right. Yeah. Okay. So let me see. a real life example would be like, well, I always go back to the grocery list because a grocery list is a set. So in a grocery list, sometimes we need like two items, two of the same thing. Um, so maybe you need 2 gallons of milk because of whatever's going on. Um, Now, for a set, we would only write gallon of milk. We wouldn't write it twice. Okay, so that would be total. So we don't write it twice. That's the rule. You only list each item once. Okay.
Okay, thank you.
Yeah, good question. Thank you, Gary. So that's a good question. That is equal. Now, the next one is a little bit confusing, so we'll spend a little bit more time on it. And it is a subset. Subset um, is, well, it has its own symbol, as you might imagine. So we'll use this symbol, which is kind of like a tipped over U. It's kind of like a capital U, but it got tipped over. Um, and this is a subset, but what on earth is a subset? It might make more sense if I just show an example and then try to give a definition. So let's say we have this set that just contains the number 1 and the number 2. This is a subset of a set that contains 1, 2, and 3. Okay. Now, what does that mean? Well, every element in this set is contained in the bigger set. Okay. So every element must be contained in the bigger set to be called a subset. So every element is contained in the set. So this is the subset. I probably shouldn't use that because that looks like it's another set. Um, so this is the subset of this set. Okay, so this is subset. Every element in this set is contained in this one. Okay, let's look at it in reverse. 1, 2, 3. Is this a subset of this set? So 1, 2, and 3 is a subset of this set, which only has 1 and 2. This is not true because this set has a 3 and this set doesn't have that. So this is not true. So this is not a subset. Not a subset. Okay. And we have to check that a lot, of whether something is a subset or not. And every element must be contained in the other set for it to be a subset. And I want to do at least one more example before we move on. And since things are getting a little crowded, I'm going to change colors. But what if I say this set, 1, 2, 3, is a subset of 1, 2, 3. Okay. Well, is this true? Is every element in this set, 1, 2, 3, inside this element, which is 1, 2, 3? Yes, this is a subset. Every element must be contained. And even though they're the exact same thing, they are subsets. So what I'm trying to say is that every set is a subset of itself. And maybe I should write that down. Every set is a subset of itself. How can that be? Because every element in the set is contained in itself. So every set is a subset of itself. So we can see the set 1, 2, 3 is also a subset of 1, 2, 3. So there we go. So these are 3 examples of what a subset is. 1, 2, all the elements are contained in 1, 2, 3, even though there's an additional element there. And then in this example, we had 1, 2, 3 is not a subset of 1, 2 because we have an additional element inside and it's not contained in the larger set. Okay, so yeah, keep an eye out for this. This is important. We want to know that. So every set is a subset of itself. Now I'm running a little short on space on this slide, so I'm going to have to move over, but we're going to continue with those ideas. And we're going to think about empty sets in terms of subsets. Now remember this, the empty set is a set that has nothing inside it, okay? So if I go back to my example of 1, 2, 3, well, I would claim that this is totally equal if I add the empty set inside it. That's okay, because there's nothing inside the empty set. There's nothing inside it, so I can always add it to a set, and it doesn't matter. It's kind of like adding 0. You haven't really changed it in any way. You haven't changed it at all. So I would say that the empty set is a subset of this set, 1, 2, 3, because all of the elements in the empty set are contained in this set. Okay, it's not true with the reverse. Most certainly, that is not true. It is not true that all of the elements in this set are contained in the empty set. That is not true. But what is true is that the empty set, all of the elements inside it, are contained within this set. And I would go a step further, and I would even say that the empty set is a subset of all sets. The empty set is a subset of all sets, including itself. Including itself, because if I look at this, are all of the elements inside the empty set, are all of them contained in the empty set? Yes. So all of the elements inside the empty set are contained in the empty set. So that is to say the empty set is a subset of all sets, including itself. Okay. So that's important to know, that you can always stick an empty set in there, just like you can always add 0 to both sides in our algebra courses. Okay. We'll talk more about that when we go over some of the homework. But for now, I think that's probably fine. So that's a little bit about the empty set and subsets. Okay. The next definition I want to go over is what the word union means. And we talk a lot about unions in this class. I always think of it as as far as sets go, and this is loosely speaking, it's kind of like adding sets together. Maybe we've heard of unions before, like work unions, teacher unions, that kind of thing. Well, what does that word mean? Is that the same as this union? Well, to unionize is to like add up to be one, right? To become one, to unionize, and that is the same thing. You're kind of adding things together, so you're adding sets together, and we will with our definition of union, we want all elements contained to be represented. Okay, and this is just going to be best if I show an example so we can kind of see what this is. So let's look at a simple example so we can kind of see if I have the set A, B, C, and I also have a set 1, 2, 3, and I should say that our union is so important that it gets its own symbol, which is a capital U. Okay, so we're going to use this symbol in just a second. So if I have two sets, A, B, C, and a set 1, 2, 3, well, if I want to find the union of these two sets, it might be written like this, A, B, C, and then this capital U, 1, 2, 3. So I tried to say that all elements contained are represented in the union. It's kind of like adding it, okay? But we have to remember with sets, we never double up anything. So how is this going to work? Well, it would just be a set that's ABC, and it also has 1, 2, 3. So now we just have a bigger set, okay? So in this example, we had two sets. There was nothing in common between them, but when we union them, now we have all of the elements. All of the elements that were contained are now represented in the union, represented in the union. In the Okay, let's do another example just to make sure that we understand that. What if we had duplicates? What if we had something that was represented? Um, let's say we had 1, 2, and we're going to union with 2, 3, 4. Okay, we're going to union this. Now I have a 2 in this left one and a left set and a 2 in the right set. Now I don't want to double count this, okay, but I do want everything contained to be represented. So it's going to be, the union would be 1, 2, 3, 4. Okay, so everything contained is now represented and I have no duplicates. Okay, and we're not actually adding the numbers. That's why I'm saying this is kind of loosely speaking that we're adding, kind of maybe compiling would be a better way of saying. If we compiled the list, um, that might be a better phrase to use of what a union is, but that's maybe how that would work. And as I was describing this, I thought of one other good example I might show you. What if it was a subset? What would happen? So let's say I had 1, 2, 3 here. What would this union look like since this is a subset of this set? The left set is a subset of the right set. What would the union look like? Well, it's just going to look like this set because all of the elements contained are now represented in the union. So it's just, we're not doubling up. Number 1 and number 2 are not represented any more than they need to be. But that is an example of how that might look if you put a union to a subset. Okay, so that might be how that looks. Okay. Now, the next thing we're going to talk about is kind of its, how do I say this? The other side of the coin, maybe. And this is the intersection. Okay, so the intersection of two sets. This also gets its own symbol, which is like an upside down U. Okay, the intersection, I always think of this kind of like I think union is adding. I think of this as in common. Okay. I think we're going to get a storm out here in Ellettsville. I just heard some thunder. So we're going to get in common. These are the items, the elements that were in common. And I might say that contained in both or all sets are represented in the intersection. of the sets. So let's do an example of that. Okay, so I think our last example might be a good one to describe intersection. Now again, this is going to be the upside down U. 1, 2, 3. Okay, so the intersection, that's what this is asking. What's the intersection between these two sets? That's like saying, what do they have in common? Well, what do they have in common? They have the numbers 1 and 2 in common. So the intersection would just be 1, 2. Okay, so that is the intersection. It's just what do they have in common, or contained in both or all sets, because you could have more than one, more than just two sets, is represented in the intersection of the sets. Let's do another one. So maybe A, B, C, D intersect with B, C, D, E. Okay, we'll work with some letters. What is the intersection? Well, that's asking what do they have in common? They have B, C, and D in common. They do not have A in common, and they do not have E in common. So we will exclude those. So those are the items, those are the elements that they have in common. Okay, we use intersection and union all the time. That's a major part of the first part of the course. But hopefully these examples are simple enough where we can kind of get a feel of what they are. And hopefully after some practice, we can keep straight um, what these symbols mean. And I guess since I have a little bit of extra space, let's do a hard one. Let's do the empty set intersected with the set 1, 2. Okay, well, okay, so the empty set is a set that just has nothing in it. And if you want, I can just rewrite this like this. Okay, so what would be the intersection, or what do they have in common? And if you remember, I mentioned before that the empty set is a subset of all sets, including itself. So it's contained. So what do they have in common? They have in common the empty set. So they have in common the empty set. So I would even go as far as saying the intersection of all sets with an empty set is just the empty set. And since I've said it, I might as well write it down. The intersection between the empty set and all other sets, and even including itself, is just the empty set. Okay, so if we have the empty set intersect with some random set, capital A, this is always the empty set. Okay, empty set always wins. Okay, because that's the only thing they have in common. Because there's nothing else inside the empty set. All right. The next thing is not it's not as widely used as the union and the intersection, but we do have to talk a lot about. It has a lot of real life applications, but it doesn't vary as much as intersection and union do, and that's called the Cartesian product. Technical difficulties. I might say that the Cartesian product is how we multiply. This is how we multiply sets. The union is kind of how we add sets together. And I would say that the Cartesian product is in a way, well, it even has the word product, which is referring to multiplying. We're going to use a capital X to signify a Cartesian product. And this will extend the list, and I think it might actually be easier if I show an example and then try to explain what it is. So let's do something kind of small, relatively small, to explain the Cartesian product, because it does get very large very fast. So we have this capital X here to signify that we're going to find the Cartesian product. We're kind of multiplying these sets, and this is how that might look. So we're going to create a new list by finding the Cartesian product. And what we do is we're multiplying, but in a set kind of way, not in the normal multiplying where 1 times 1 equals 1. No, this is like with sets. So 1 and 1, if we multiply this, this is going to come up with the pair 1, 1. So that would be the first pair. If you remember your algebra class where you're like distributing, with sets, you're like pairing them together. So 1, 1 would be the first one, and then 1, 2 might be the second one, and then 1, 3 might be the third one. And so we have all the ones for the first one here. So we have all those connected to this. And now we need to worry about the twos. So we'd have 2, 1. Okay. Then we might have 2, 2. And then we might have 2, 3. Okay. Yeah. So this is the Cartesian product of, sometimes in math classes, this is called the cross product, but we don't really need to, we don't call it, we call it Cartesian product in this. And this is kind of how you would multiply lists. You might also think about it, how you could pair people up. If instead of 1, 2, 3, if those were a list of people and you were paired up, then you could find all the pairs. If you cared which order they're in, you could find how you might pair these people up. So we're coming up with pairs. So this is how you kind of multiply sets. So it's a ordered pair of the contained sets forming a new set of those pairs. Okay. So again, this is much easier to describe just by showing an example than trying to describe it in a sentence. But it's kind of like how we multiply sets. Let's do another example. So let's say we have A, B, C, and we're going to multiply this by the I don't know, let's say D and E. Okay, so let's see how we might do this. So we have A, B, C, so we have to pair everybody up. So first it's going to be A and D, and then you have A and E. Don't forget the comma inside. You have B and D, and B and E, and then you'd have C, D, and I have an extra comma there, and C and E. So this would be the Cartesian product. And one thing I want to mention, I'll probably mention it again, and that is the number of pairs it's going to come up with is the number of elements that it has inside. So for instance, maybe I'll do a different color. There are 3 elements, and that might not show up that well. So there are, let's do orange. There are 3 elements in this. There are 2 elements in this. So if we multiply that, we should get 6 elements. 1, 2, 3, 4, 5, 6. So that's a way you can check if you have 3 elements times two elements, you're going to get 6 pairs there. Okay, 6 pairs. So you can find that, or maybe you're just interested in how many pairs you have. There's a homework question where you don't actually have to find the Cartesian product. You just have to state how many pairs there would be. And so you can just multiply the number of elements inside to find that. Okay, so that's Cartesian product. Um, we talk about it a little bit, but it's not as interesting as, say, union or intersection. There's not quite as much we can do about it. So we kind of talk about it and then let it go. So the next thing I think we need to talk about is we need to talk about the universal set and complements. So we need to talk about those. Those are very important. So the universal set is, oh, I forgot my little symbol. So for the universal set, it's a little frustrating. We also use a capital U for the universal set. I'm going to try to always remember to put this little bar up top when I'm talking about universal set as opposed to union, but the universal set is just another capital U. And the universal set is kind of like the universe. It's the set that contains all elements. Okay, well, what on earth does that mean? Okay, so let's look at an example. If I have a set 1, 2, and I have another set that's A, B, and I have another set that is, say, 1, 3, then what would the universal set equal? Well, the universal set is going to be the union of all the sets, all these sets here. So it's going to be the union of all sets. It's going to be a set that contains all of the elements. So we can write that out, but it's going to be just all of these, the union of all of these sets. So A, B, unioned with 1, 3. Okay, so the universal set, try to always remember to put that bar there, is 1, 2, and just to put them in order, 3, A, and B. So that would be the universal sets, okay? Now, you should also see that these are subsets. These are subsets of the universal set. So 1, 2 is a subset of the universal set, okay? So yeah, so the universe, all the sets are going to be subsets of the universe because it contains everything, and even the universal set is a subset of itself because it contains all the elements of itself. So the universal set, maybe I'll phrase it a little differently. Oops. I think I want to say all sets are subsets of the universal set, including the universal set, because all of the universe is contained in the universe. Okay, so that's the universal set. We will talk more about that when we show some of the homework problems. Okay, but the next thing we need to talk about is complements. Okay, and then once I introduce the complement, I can then explain one more thing about the universal set. So a complement of a set, we're going to use a little apostrophe to signify a complement. So say we have a set A, then we will have a little apostrophe here to mean the complement. And the complement of a set is it's all of the elements in the universe not in A. So another way, sometimes we say it is not A or not in A. Okay, not in A. That is the complement. Or we might also say that the complement are the elements in the universal set that are not in A. That would be a complement of A. So let's look at an example so we can clarify what we mean by a complement. So first I'll have to define what I mean by A. So let's come up with an example. A simple one might be 1, 2, 3. Okay. Let's talk about the universe. Let's set up a universe. So maybe we have 1, 2, 3, 4, 5, A, and B. Okay, so what is A complement equal to? We use this apostrophe to mean this means not A. So what does this equal? Well, A complement is all of the elements in the universe that are not in this A. So I have 1, 2, 3 in A. That's this part here. And all of the rest of the universe is going to be what not A is, the complement of A, which is 4, 5, A, and B in this example. So in this example, that would be 4, 5, A, and B. So that would be the complement of A. Okay. So the elements that are in the universe but not in A. Okay, so that's what the complement is. Another statement I should say is that if you add, or I should say unionize, A unionized with the complement will always equal the universal set. Because this is like saying if you add the elements in A with all the elements that are not in A, well, that would be all of the elements there are. So this is a little truth tautology right there that is true for all sets, no matter what they are, even the empty set. If you add all of the elements and then all of the elements that are not contained in it, that must be all the elements there are. A real life example might be if you think of yourself and then you think of every person, every other person that's not you, well, that's everyone, right? The complement of you would be everyone other than you. And so if you put those together, that's everybody. So that is a complement in terms of how Finite thinks of it. Okay. So hopefully that makes sense what we mean by complement. Sometimes those can be tricky, especially when we combine them with other ideas. But the complement is really just, we need to make sure we understand that this is not an A, the opposite of A. Okay. The next thing I want to talk about is it's kind of a formula, and it's called De Morgan's law. So De Morgan's law is a result that are very, it's kind of a formula, but it's an important formula that contains information about every set there is. And the De Morgan law, we're going to have a couple different versions that I'm going to show you. And that would be A unionized with a set B. If we complement that, that would be the same thing as A complement intersect B complement. Okay, so this is De Morgan's law. I'm just stating it as a fact right now. I'm going to write out the other version that we might use. A intersect B complement equals A complement unioned B complement. So these are De Morgan's laws. Okay, we're just going to state them as a fact, but hopefully through some examples, we'll see that, yeah, this has to be true always. Okay. Now, don't forget this U symbol here. This is not the universal set. This is the union. And this is saying that the union of A complement, that's what we mean by this apostrophe, is the same thing as the complement of A intersecting the complement of B, okay? If you've taken algebra recently, then you can kind of think of it as we're kind of distributing the complement. And so the complement of A, the complement of a union would be the intersection. It's kind of like the opposite, and then the complement of B here. Or you can look at it the other way, where A intersect B complement. If you distribute that complement, the opposite of A, the opposite of the intersection is the union, and the opposite of B. Okay, so these are De Morgan's laws. We're just going to state them as a fact, and now we're going to look at some examples to see whether or not that they are actually true. So let's come up with some examples that we've used a little bit before. So let's come up with one. I should define this as A. A equals 1, 2. B equals 2, 3, 4. And so the universal set would equal 1, 2, 3, 4. Okay, this should be enough to show an example of De Morgan's law. Let's take a look at this first one up here and see what that even means. What is A union B? What would that even be in this example? Well, A union B is everything in A and everything in B. We just don't want to list anything twice. So A union B is 1, 2, 3, 4. Okay. Now this first part is talking about A union B complement. So it's the items that are not in this. So we want the item in the universal set. And maybe I'll add another item. That might help. Let's add it 5. So if we add a 5 there, then we can have something other than the empty set. So if we have A union B, we see that that's 1, 2, 3, 4, because those are the items inside B. Now, if we have A union B complement, well, that is the thing. We want the opposite of the union. Okay, so what are the elements that are outside of this set? And that would be 5. So that would be the set 5 there. Okay. Okay, let's see if we can find what this means. A complement, what is that? Well, A is 1, 2. So what are the items that are in A complement, not A? Well, it looks like they would be 3, 4, and 5. Okay, these are the items that are not in A. That's what A complement means, okay? And it looks like we're going to need that there. What are the items that are in B complement? Okay, these are the items that are not in B. What are we missing with B? We have a 1 missing, and 2, 3, 4, and we also have a 5 there. Okay, now, so there's A complement, there's B complement. Now, this is talking about the intersection, so let's see what that would be. The intersection is what they have in common. Okay, so what do these two sets have in common? This one has a 3, but this one doesn't. This one has a 4, but this one doesn't. This one has a 1, but this one doesn't. So they only have a 5 in common. Okay, and we can see, yeah, these are the same thing. Okay. These are the same thing. They both equal the set with just 5. So it turns out De Morgan is right. So we can distribute that complement sign and just that way, okay? So that's kind of cool. Now, in other programs, I can copy this. I kind of want to just edit it, but I don't think I can do that. I'm just muttering to myself at this point, but let's do this one because I think we can maybe squeeze it in there. So what is A intersect B? What do they have in common? 1, 2, 2, 3, 4. So they just have a number 2 in common. And this is talking about, oops, this one is talking about A intersect B complement. So we want to talk about what is the complement of just number 2. Well, that's going to be 1, 3, 4, 5. Okay, so that's the left hand of this. We've got that covered. And we already have A complement and B complement already listed there. So if we union those, and that's what this right-hand side is talking about. So A complement union B complement is just the union of these. So we can see that that's going to be 1, 3, 4, and 5. And we see that, yeah, they do equal each other. These are the same thing. Okay, I'll circle that in blue. Okay, so that's an example. We can kind of see De Morgan's law, how they work. We're going to look at more examples in just a minute when we actually look at the real homework. But this is just kind of an example to get us going. If you have any questions so far, this might be a good time to ask me a question. Because I'm just looking through my lecture notes just to make absolutely sure that we're ready for the real homework. I think I covered all the definitions.
I have a question real quick.
Yeah, yes, please.
The De Morgan's law, are you always trying to prove that they're the same thing then?
That's an excellent question. It I let's put it this way. I'm always trying to prove that they're equivalent. There will be instances in the homework when we get to the homework, we'll see it. That it will be easier to find one side of that equation than it is the other. And since they're equal, well, then we can just simply find the easier one than the other one. And yeah, so we will see that okay, well, this is equivalent by De Morgan's law, and this is the easier one to find by the information given. So then we can use De Morgan's law to kind of make our life a little easier. So yeah, that's a good question. In the actual homework, it'll never be explicitly asked, prove that De Morgan's law is true. We're kind of saying it is true, and now you can use it to your benefit if it's easier to find one side or the other. Later tonight, because hopefully you guys remember this is a 3-hour class. So in the second section, we're going to look at visual examples that we call Venn diagrams, and we'll actually be able to visually see that De Morgan's law is true just by shading in certain regions of circles. We'll see that that's true. So yeah, excellent question. It has to do with, well, we're stating that it's true, and then we can easily use it to our benefit because it is a true statement. Excellent question. Okay, so I think that is all of the definitions I need to define before we just look at real homework questions. Yeah, I think we're good. So I will save that. I will save those lecture notes. Those will be posted tonight in the 1.1a discussion section. I'll post those tonight. But right now, I want to actually show some real homework that you guys will have to do either tonight or tomorrow or the next day. But let's